right, so next is Soumith Chintala from Facebook AI Research New York on how to train a GAN.
Hello. That's a lot of people. So I'm going to I give a short talk, 30 minutes, on how to train a GAN. I won't actually tell you how to train a GAN. It's more like I will tell you all or some of the missing details that all research papers omit, because it does not fit into the story. But if you start to train GANs, you would need to know some of these things. In the past, for example, many people used to use, many people use gradient clipping in training RNNs, but for quite some time, I think that detail was skipped. And there's many details that are skipped. So similarly for GANs, I'm going to give some details that are helpful if you start researching in GANs. So GANs are like a house of cards at the moment, where there are many moving parts. There's not a good way to validate whether you're doing well on your, whether your generator or discriminator are doing well or not. And if you change many of the moving parts, your generator and discriminator collapse and nothing works. And I think as a field, as a subfield, adversarial networks, it's a very early algorithm, and improvements are being made to stabilize GANs in various ways. But as we go forward, we have to use some of the hacks I do mention. So Ian Goodfellow and his colleagues came up with GANs in 2014. I do not know how much blood and sweat they had to sacrifice for getting the GANs to stabilize and train properly. But when we did our paper, Lab GAN in 2015, we had to do quite a few things to actually get GANs to start training, produce image samples, and so on. So some of the funny things we did was we actually, if you look at our source code that we released, we have a model generator that would literally generate new architectures that are combinations of different convolution layers, different feature maps, and so on. And we threw different models at the cluster, and we would visually inspect whether the produced images looked real or just looked like noise. So visual inspection was a big thing because in adversarial networks, at least yet, there is no way to correlate the loss of the discriminator with whether your sample is, whether your GAN game is working to produce samples that look like your real distribution or not. So we had looked at thousands of images and tried to compare them to the real samples. And we did have countless hacks that we tried, heuristics, as you may also call them, that tried to stabilize the GAN game. And we also just built our research on hope, like we all do. But then later in 2015, so Alec Radford and Luke Metz, every weekend while they were working at their startup, they would quietly hack away on trying to find more and more stable GANs. We had a paper that was published at iClear that stabilized GANs to a much greater extent than it was before. People could actually take a DC GAN and they could simply plug it into their favorite image data set, and you would get reasonable samples. And if you can clone Alec, you could probably get a good, you don't need this talk, but since Alec is only a single person and he found DC GANs, but they also have issues, the community came up with more and more heuristics and hacks. And in 2016, folks from OpenAI came up with more heuristics and more stability hacks. I think they proposed 4 or 5 different ways to stabilize GANs even further. And at the moment, this looks like the state of the adversarial networks in terms of stability. And if you use all of the tricks that are in these papers, as well as some of the tricks from the talk, I think you will have a reasonable experience with training your own GAN. And just a quick comparison to how, why GANs might be slightly different to build intuition upon or build new heuristics or hacks upon. GANs, as I said, don't have an objective validation score you can use to know whether your model is working or not. So, and also the intuitions you developed around GANs are generally poorer than when you build a connet, for image classification or so. And at the large part, a lot of theory is being developed around GANs to try to improve the situation, but right now it's throw things at the wall and see what sticks, I think, for the large part. So I'll have a series of tricks. Each slide is one trick, I guess. And the first one is simply the basic data science thing, normalize the inputs between -1 and 1, but also the generator's output bound it to be between the same bounds. So usually we add a tanh layer to the output of the generator. That's a simple one. The second one is something that you usually do not see in the papers, but if you actually go look at the source code, you would end up seeing, is that you actually, everyone in practice, or most people in practice, use a modified loss function. Usually in papers to optimize G, you say, okay, you minimize log of 1 minus D, but in practice, what you end, like I've seen a few implementations of GANs in various applications, and what you actually end up doing is when you're training the discriminator, so let's say the target label for discriminator is 1 and the target label for generator is 0. When you train a discriminator, you keep those target labels as is, but when you train the generator, you simply flip the target labels. And this is quite important because the loss function that's given in the original paper, in fact, there's a note in the paper that hints to this, is that the modified formulation has more stability in the gradients when you're training and in the initial part of the GAN process. So next trick is your latent Z vector that you give. You would want to make it a spherical Z rather than, let's say, a uniform, drawn from a uniform distribution or something. And also, when you are trying to sample new images or trying to do interpolations between 2 points in Z, then you would want to actually take all the intermediate points that you're trying to generate between two points in the latent space. You might want to take the great circle when you're sampling all these intermediate points rather than just taking a straight line between these 2 points. This is a mistake we did do in the DCGAN paper, but Tom White has an excellent paper that that kind of tells you, gives you a few more things to do properly when you're sampling images, especially interpolating images from adversarial networks, from the latent space when you're trying to do this at test time. The next fourth trick, a very important one, that you will almost always encounter and scratch your head and not know what happens, is using batch norm properly. So usually at this stage it is recommended that in adversarial networks and both the generator and discriminator you do use batch norm, but one thing that is usually skipped is how to use batch norm properly, which is kind of counterintuitive. Basically, what you need to do is, when you're training the discriminator, you give a whole batch of real samples to the discriminator, or give a whole batch of generated samples. You never mix the mini batch with some real and some fake. And we learned this by accident when we were re-implementing some code, and suddenly things didn't work. And it's counterintuitive in the sense that you would expect that batch statistics are easier to help the discriminator quickly get stronger when it's in the initial stages of playing its adversarial game. But somehow this seems to work. And some people, some that are not me, have better intuition on this. The fifth trick is to try to avoid sparse gradients. So usually you wouldn't want to use max pooling or just hard, like just ReLU, the plain hard ReLU. But you would want to use softer components, components that have more soft gradients in your network. For example, you would try to use leaky ReLU, and also when you're downsampling, instead of max pooling that you commonly use in classification networks, you would use average pooling or strided convolution. And when you're upsampling, you would use a transpose convolution with a fractional stride, or you would use kind of like simpler upsampling that gets rid of aliasing artifacts. I call it pixel shuffle because that's what the Twitter guys called when they published their paper referencing this. I missed a reference here, but I will probably add it to the slides later when I post them online. This seems to be important. The intuition here seems to be that sparse gradients are generally not as nice for generative models as they are for discriminative models, or like components which have sparse gradients in the backward. And in practice, this almost always seems to be true. And next is a sixth trick that Ian definitely covered in his talk on Monday, which is to do label smoothing. Almost everyone who does a non-trivial GAN uses label smoothing of some sort. So label smoothing means that instead of having hard labels of let's say 0 for real and 1 for 0 for fake and 1 for real or something, you instead soften the labels by giving a stochastic value to the real label between, say, 0 and 0.3, and stochastic value to the fake label to be between, say, 0.7 and 1, and so on. And another thing that Emily Denton had told me about was that you can also make the labels noisy for the discriminator, which means that occasionally with some probability of p, you would flip the labels and somehow that injects some kind of constructive stochasticity into your network. And I think like a few people use it. Michael Matthew used it as well in his video prediction GANs, I believe. And next, if you can, if your problem fits within the image domain, you should use some variant of DC GANs because they generally work and they wouldn't waste your time. But if you can't use DC GANs, let's say you're taking a pre-trained model and trying to improve it with a GAN loss or something, then what you would want to use is a hybrid loss that is, say, a GAN loss combined with some L2 Euclidean loss, or a hybrid variational autoencoder plus a GAN, or so on. And I think many papers that appeared in recent times that have gotten quite some attention have done this. The image in painting paper from Pathak et al. And from Berkeley, the video prediction stuff from Michael Matthew, I think a few others, they have used a KL term somewhere along with the GAN. And it's not a bad thing to try. And next is you can draw a lot of tricks from reinforcement learning. I think RL is also, in general, a very, very stochastic optimization problem where you have lots of instability. And you can read David Faust's paper that appeared recently that tries to draw parallels to actor-critic models and GANs, and they have a nice table that kind of shows like what RL tricks that are used for stability can also probably apply to GANs. And in practice, we have definitely seen that things like experience replay do help in stabilizing GANs. You can, for example, either keep past generations and occasionally show them to while you're training your discriminator. What you can also do is have past models of past checkpoints of your generator and discriminator, and occasionally swap those out with the current parameters and train a few iterations. Both of these do help. Coming to the optimizers, Adam seems to be the most popular and stable optimizer to use for GANs, usually with like everyone kind of uses the same learning rate of I think 0.002 or something. You can look at the DC GAN paper for the exact details. In fact, like the beta 1 and beta 2 can also be like hard-coded to a particular values, and this optimizer kind of works everywhere. Alec Radford found it, I don't know, either through trying everything or just by magic. And one thing Michael Matthew did say was that he found that using SGD while you're training the discriminator, but using Adam while you're training the generator seems to magically help as well. Now, I don't even know what kind of optimization that is, or like if you can draw any theory to it, but yeah, it works. Next is if you want, like one important thing is you want to track failures early. That is, if your GAN is not working, you want to know that early. Usually, if your discriminator loss quickly goes down to 0 or eventually goes down to 0, that's a sign of your adversarial network never doing the right thing. Also, check the norms of the gradients. They're a good sign of knowing what's going on. And one thing Martin Arjowski told me was that he seems to have found in practice was that when things are working, the discriminator loss has lower variance. I have not verified or used this thing myself. And if the loss of the generator steadily decreases, somehow that means that it's fooling the discriminator with just like garbage noise, and like the whole problem has collapsed. This is also a trick that Martin mentioned. And the next trick, this is something almost every one of us who's played with GANs has tried. And if you try it without any theoretical backing, if you just like try to see if you can find a heuristic, just an advice, almost all of us have tried it and it fails, which is trying to find a schedule between optimizing the discriminator and the generator. Let's like say, oh, if the discriminator loss is above a certain value, let me optimize the discriminator a bit more until it gets stronger, and then once the generator loss goes above a certain bound, I would want to optimize the generator down so that it gets a bit stronger, and trying to keep this equilibrium by finding a heuristic to optimize the discriminator and generator schedules using their losses or their gradient norms and so on. A few people have tried it. I think if you are also going to be the next person trying it, have some kind of theoretical backing on like why you're trying it or how you're trying it. The next trick is that if you have labels, use them. Like let's say you have a semi-supervised data set, have some auxiliary classifier that would classify your real samples, and also have a separate like GAN loss as usual. And it seems that having any form of semantic labels does help. I think like the plug-and-play adversarial net. I mean, there's several papers that use labels. All the conditional GANs which have showed impressive results have used labels. And this is something that has been proposed at the same time by Ferenc Kozar and Martin Ojewski. And also we found hints of this in the code for improved GANs, but it did not go into the paper. It was commented out, which is that you add noise to the inputs, some kind of noise. Let's say you draw some Gaussian noise and add it to both the real and generated samples, and you decay the amount of noise you add over time. And there's more theory in both Ferenc's post and Martin's paper on why this might be useful, helpful. Another thing that you can do is not just to the inputs to your discriminator. You might want to add noise to every layer of your discriminator, every intermediate layer as well. I think this was either done by Jigsaw in the EBGAN paper, or he did mention that he has done it post-paper. And that's something that also has been found in the improved GANs TensorFlow code. The 14th and second last trick is train the discriminator more sometimes when it's convenient. Like the last two tricks are like mixed results, so take them with a pinch of salt. So basically the idea is that you want to train the discriminator for every iteration of training the generator. You want to train the discriminator k times, and k is determined by you by experimentation, and it seems that that would help. How you would find k is unclear, and it's left as an exercise to the reader. And then the last one is batch discrimination. Basically, the idea boils down to, instead of classifying a single sample as real or fake, you would want to classify a whole mini batch as real or fake. The actual formulation is slightly more complicated. You do a random projection, and then you do pairwise distances, and then you do something. It's in the OpenAI's improved techniques paper. It has worked for them. It has worked in some cases for me, and it has not worked in some cases for me and a few others. It has mixed results. It's unclear why this is so, because generally, on principle, this thing should work. Lastly, quickly going over one trick for conditional GANs. This is something that Michael Matthew had suggested. Discrete variables, let's say you want to condition upon not just other images or continuous variables, but you want to condition upon discrete variables like text or so. Then you send the discrete variable into some embedding layer that's like a lookup table that for each variable, each discrete value, it would return some embedding, some, say, 128-dimensional embedding or so. And then you upsample the outputted embedding to the size of the image, a single image channel, and then you simply add those as image channels to your discriminator generator or the generator and discriminator input, and keeping the embedding dimensionality lower and not matching it with the size of your image channel directly seems to be important, mostly probably because like it just increases the number of parameters in the system by a lot. So with that, I conclude this talk, which has all kinds of hacks and zero science. And the conclusion is that in the community, like many people are exploring GANs from a theoretical perspective, and also like, you know, generally kind of real science is being done. But hacks are a stopgap, and hacks kind of have to be used at the moment if you want to get into GANs. Like, for some reason, everyone wants to, like a lot of people want to use GANs, they just don't know that they're unstable until they get into using them, and then they're kind of stuck there. So, yep, if you guys have any questions, feel free to ask. No theory questions, please.
I have a question here. Right.
Yes.
So I'm just curious about what the discriminator network scores become for those like weird ImageNet like pictures after the training.
The discriminator networks what become?
The score, like, you know.
The score. Yeah. Usually if you have a stably training GAN system, then your discriminator is hovering around 0.5 probability. Like it never can tell real from fake.
But it even gets confused to those weird ImageNet like pictures. Okay.
On your last slides about conditional GANs, and you mentioned that adding the conditions on the convolution as additional dimension something. But on the Scott Ray's conditional GAN paper, and he basically adding the maybe captions condition on after the noise concatenated with the noise sample.
Right.
So which one is better, or you should add in both, or you should just do one?
Try both and see which is better. I guess.
Okay.
Question. In the trick that you present, here. Hi.
Yes. Hello.
Hi. Yes. In the trick that you presented, that in order to use well the batch normalization, you put on the same batch just images that the discriminator accepts as fake or not. Yesterday I heard about this weight normalization, and they talked that one of the problems of batch normalization is the added noise. Yeah. Did you guys tested this new weight normalization idea while training those GANs?
It might be a good idea to try. It's just like a very new paper, I think, weight normalization. Certainly, there could be a new paper, weight normalized GAN, which you write. Like, I think it's a good idea to try. Like, I don't think anyone has got into it yet. When batch norm is not usable in your situation, some people use instance normalization. That is just from your inputs, you subtract mean and variance. In that particular instance, I do not know anyone who tried to use weight norm yet.
When you're embedding your inputs, is it better for both models to share an embedding, or do they each get their own?
They share an embedding.
Is it a good idea to use pre-trained discriminator and train it also in the process along with generator? Or we should initialize generator from, I don't know, from random?
So I think there's evidence, depending on the problem, there's evidence for both. Like if you want to train GANs in an unsupervised setting and your goal is to do unsupervised learning, then you obviously want to train both of these things from scratch. But if you're trying to do conditional GANs, then you could probably use like pre-trained discriminators or some kind of pre-trained features from models and so on.
Okay, I have a question here. So on conditional gain, you mentioned that I haven't tracked this literature, but I trust what you said. The label is embedded as part of embedding in the middle. But I think more natural way of thinking that is that to put a label in the output. So rather than having binary in the regular gain, fake versus real, you might have multiple label with another label could be the fake. How could that compare with the embedding way of doing conditional gain?
I think both. Like I did mention that as well. Like if you have labels, you should use them with an auxiliary classifier, and it seems to be very useful to do that.
Okay, but on the other hand, if you do that, then the fake is one of many classes. So that kind of dilute the original gain that distinguish, just one true versus one fake. How could that information be sort of diluted in terms of distinguishing between fake and real? That's sort of thinking.
I don't know either.
No? Okay, thank you.
Yeah.
Oh, just quickly, sorry. So you mentioned a lot of hacks, and I think they'll be really helpful for trying to implement GANs. But if you could sort of focus on one where you think some theoretical prospects would really help us remove the hack and get farther, which do you think would be?
The first thing we would focus on is to figure out how to know that the GAN is training or not, instead of staring at samples. So trying to have some correlation, trying to find some reformulation of GANs where you can have a correlation between the loss and the samples, or the problem you want to try to solve. That would probably be helpful. Yeah.
Okay, so we have a 25-30 minute coffee break now to be back at 11 o'clock. Let's thank Soumith again.